So now that we've gotten the idea of Pca, let's see how singular value decomposition helps us to accomplish it. It's basically one method to calculate the orthogonal decomposition required in Pca, and it's nice because we can obtain the capital K largest eigenvectors and values directly, and because it can work with all different types of matrices, not just ones that are square, which our other factorizations require. To understand SVD, it helps to think about its geometry of what it's trying to do, and this is applicable in the square case, although it's helpful to understand overall. The idea is that we have original data that we want to transform in some way, using a transformation M to get data output. But what we want to do is decompose it into three component transformations: a rotation V, which is finding our principal components, the orthogonal bases that we need, followed by the scaling by our eigenvectors, followed by the projection of all of the data into the weight matrix space. So the idea of singular value decomposition is to represent the matrix with atomic operations of the weight matrix times the singular values times the singular vectors. We can see this here, where we first have the weight matrix, where each row in the weight matrix represents a particular point, let's say J, as represented in the dense eigenspace. This is multiplied by the singular value matrix, which is a diagonal matrix with zeros on the off-diagonal entries. The most significant singular value will be located in the top left corner, which will have the largest eigenvalue. The least significant eigenvalue that contributes to the reconstruction of the original matrix will be located in the bottom right. In singular value decomposition, we don't calculate the matrix all the way out until we have all n components, but stop at some capital K value. Finally, we have V transpose, which is the singular vector matrix, where each row is an eigenvector. We're going to calculate capital K of these eigenvectors to represent the dataset overall, and to reconstruct X as X hat. We can see how this would look when we have the full matrix and we don't approximate it using a smaller rank. We would have all of the extra dark green components for the U and sigma matrix, and our V transpose would be full rank of n by n. Now we can contrast this with the Pca algorithm in general, where we're implementing the Pca using SVD. We have the same steps as in the first three steps, where we take the data matrix and normalize it. We then call SVD on the normalized matrix XC and ask for the K largest singular vectors. What's being returned to us are going to be the vectors with the highest singular values, which are rows of the V transpose, where the coefficients Z are going to be derived from the U times the singular value sigma matrix.